Hello everyone and welcome to Infotainment Lounge. Today's video is about the reactions of halogenoalkanes. If you can see me, please say something in the comment section so that I may know that you are watching me. The stream is on. Okay, let's start. Now before starting the reactions of halogenoalkanes, first I want you to get familiar with the classes of halogenoalkanes. Halogenoalkanes are actually divided into three classes. And the three classes are primary halogenoalkanes, secondary halogenoalkanes, and tertiary halogenoalkanes. Okay, now primary halogenoalkanes. See, halogenoalkanes, for all the halogenoalkanes, what is their functional groups? The functional group is the bond between a carbon atom and the halogen atom. Like if we represent halogen atom as X, then C single bond X. This is the functional group of halogenoalkanes. Now, this carbon atom, all the carbon atoms always form 4 bonds in total, and this carbon atom has already bonded with one halogen in this functional group. But there are still 3 other bonds of this carbon atom. Now, what type of radicals are bonded to these 3 bonds? That determines the type or class of halogenoalkanes. Like if a carbon atom involved in the functional group is bonded to 2 or 3 hydrogen atoms. If all these bonds are bonded to hydrogen atoms or 2 of these 3 bonds are bonded to hydrogen atoms, then the halogenoalkane is a primary halogenoalkane. For example, see, this is chloromethane. And in this compound, this carbon atom which is involved in the functional group, which is the only carbon atom, is bonded to 3 hydrogen atoms. So chloromethane is a primary halogenoalkane. Let's take another example. See, this is chloroethane, and in this compound, the carbon atom involved in the functional group is bonded to 2 hydrogen atoms, which means again it is a primary halogenoalkane. But if the carbon atom involved in functional group is bonded to only 1 hydrogen atom, in that case the halogenoalkane is considered to be a secondary halogenoalkane. For example, this is a compound. Its name is 2-chloropropane. Now, if you see at this compound, see the carbon atom which is involved in the functional group is bonded to only one hydrogen atom. On the other two sides, there are carbons. So this means this halogenoalkane is a secondary halogenoalkane. Let us now consider another situation when all three of these bonds are involved in carbon to carbon bonds, like there is no hydrogen attached to the carbon atom involved in the functional group. In that case, the halogenoalkane is considered to be a tertiary halogenoalkane. Let us take an example. Again, I am drawing the displayed formula of a compound. Now, if we name this compound is called 2-methyl-2-chloropropane. And the carbon atom which is involved in the functional group, this one in the middle, this carbon atom is not bonded to any hydrogen atoms, it is bonded to carbon atoms from all three of the sides. That means this halogenoalkane is a tertiary halogenoalkane. Okay, there is a question. Can the number of chlorine atoms involved change its class because number of hydrogen atoms could be different? See, first thing is that I gave you example involving chlorine atoms only. There could be any halogen atom, it could be bromine, it could be iodine. Second thing is there would be, if there are two halogen atoms, suppose two chlorine atoms in the same molecule, and they are at different positions. Now, that would show the presence of two functional groups, because C single bond halogen atom is one functional group. So there would be two functional groups in that. So each functional group would be classified according to these rules. See, one of them may be a primary halogenoalkane functional group and the other one may be a secondary halogenoalkane functional group, or both of them may be secondary or primary or tertiary halogenoalkane groups. So you have to classify each of the functional groups present in the molecule if there are more than one functional groups present. Okay, now moving on to the properties of halogenoalkanes. Okay, now first thing, that their melting and boiling points are higher than those of alkanes and alkenes. That doesn't mean they have very high melting or boiling points. They still have low melting and boiling points. But this is just a comparison to the other homologous series that we have studied so far. Their melting and boiling points are a little higher than those of alkanes and alkenes. And the reason behind that is presence of a polar bond. See, carbon to halogen bond is always a polar bond, and these bonds form permanent dipoles. So the force of attraction between the molecules would involve the permanent dipole attraction, which is a relatively stronger force of attraction as compared to van der Waals forces, which are present in alkanes and alkenes due to their non-polar nature. So they have relatively higher melting and boiling points because of presence of permanent dipole force of attraction. And in reactions, you can use the state liquid for halogenoalkanes. They are mostly liquids at room temperature. At room temperature and pressure. But another thing you need to remember is that halogenoalkanes are volatile liquids. They are highly volatile. They are much more volatile than alkanes and alkenes. They are so because of their volatile nature, we have to alter some of the conditions of their reactions. We will deal with those conditions when we go to the reactions. So moving on with the properties. Okay, they are mostly non-flammable. Non-flammable, that means they do not catch fire, they do not undergo combustion reaction under ordinary conditions. And in fact, because of this property, they are used as fire retardants. They are used in fire extinguishers. We have a question. Most of them are liquids due to similar reason to that in alcohols. Yeah, actually a relevant reason, not the exact same reason. In alcohols there is hydrogen bonding. In halogenoalkanes there is permanent dipole force of attraction. So there is a difference of the type of force of attraction, but rest of the thing is the same. So it is there is a similar explanation to that. I'll give you a few seconds to note this down, then I'll move forward. Okay, so now we can proceed with the reactions of halogenoalkanes. Now, as I have already told you that halogenoalkanes are not flammable, they are non-flammable. So we are not going to study any combustion reaction when we are dealing with the reactions of halogenoalkanes. They do not undergo combustion under ordinary conditions. So what they do is they take part in several other types of reactions. One of them is substitution. Now, different radicals may be substituted in halogenoalkanes. We will deal with each one of them one by one. Okay, we have another question like what if one carbon atom is bonded to two halogen atoms? What will be its class then? Suppose this is the molecule, there are two halogen atoms and two hydrogen atoms. Now you have to check each functional group one by one. First, let us check this functional group. So according to this functional group, this is a primary halogenoalkane because the carbon atom involved in this functional group has two hydrogen atoms bonded to it. And same is the case with this functional group. When you analyze this functional group, again the carbon atom involved in the functional group is bonded to two hydrogen atoms, which makes this functional group primary halogenoalkane as well. So in respect to each of the functional groups, this is a primary halogenoalkane. But if we are talking about 1,1-dichloroethane, in terms of each of the functional groups, this halogenoalkane is a secondary halogenoalkane because one hydrogen atom is bonded to the carbon atom involved in the functional group. See, this primary, secondary and tertiary halogenoalkane category is classified in terms of hydrogen atoms which are bonded to the carbons which are involved in the functional groups. And if there are more than one functional groups, it doesn't matter if the functional groups are present with the same carbon atom or different ones, you have to analyze each functional group separately. I hope that answers the question. Okay, now moving on to substitution reaction. Substitution reaction, you already know that what substitution reactions are. When one atom or a group of atoms replaces another atom or a group of atoms from an organic compound. When it displaces another atom or a group of atoms, it is called substitution reaction. In inorganic chemistry, when any radical replaces another radical from a compound, that is called displacement reaction, like more reactive metals displace less reactive metals from their compounds. But in organic chemistry, when any atom or a group of atoms replaces another atom or a group of atoms from an organic compound, that reaction is called substitution reaction. Now, there are different radicals which can be substituted in halogenoalkanes. One of them is OH group. Okay, now the reagents needed for this reaction, the reagent needed for this substitution reaction, substitution of OH group in halogenoalkanes is aqueous sodium hydroxide or aqueous potassium hydroxide. We could use either of them, but this sodium hydroxide or potassium hydroxide being aqueous is very important. You must state the term aqueous when you are telling the reagent for this reaction. Why is that very important? You'll know when we deal with a few more reactions of halogenoalkanes. Okay, now the conditions needed for this reaction are heat under reflux. See, if you are already familiar with this term, reflux, it's very good. But if you are not, I'm going to give you a little explanation of that. See, for example, if we are carrying out the reaction in this round bottom flask, we have added the reagents here. The set of reagents are present right here, and we are heating this reaction mixture from the bottom. Now, why are we heating this from the bottom? Because heat is necessary for the reaction to take place. If we do not heat this mixture, reaction will not take place. But there is a little problem. As I told you earlier, that halogenoalkanes are highly volatile liquids. So when we start heating them, they will evaporate. So we don't want them to get out of the reaction mixture, because we want them to react with the reagents that we have added. So in order to do that, what we can do is that we can place a cork at the top of this round bottom flask, and we can place a condenser. We can connect a condenser to this cork. Okay, now this condenser, it has two tubes. One is the inner tube, which is connected to this reaction mixture, the reaction chamber, and there is an outer tube which is filled with cold water. Here at the bottom opening there is an inlet for cold water, and at the top there is an outlet for cold water. That means cold water is continuously running through this condenser. So it is continuously filled up to this mark with cold water. What does that do? It reduces the temperature of the inner tube. So now the vapors of halogenoalkanes which started escaping from this reaction mixture, they do not have any other place to go but into the condenser, into the inner tube of the condenser. And when they move into the condenser, the inner tube of the condenser, they face a low temperature. At that low temperature, they condense, they turn back into liquid form, and those liquid droplets start falling back to the reaction mixture. This is how we do not let the volatile liquids escape from the reaction mixture, and the reaction is then completed. This is the operators for this thing, heating under reflux. You can draw this diagram if you want to for your reference. So guys and girls, let us move on to the reaction. Now in this case, we are dealing with the substitution of OH group in a halogenoalkane molecule. Suppose we are talking about C2H5Cl. This is chloroethane. and when we react it with aqueous sodium hydroxide or aqueous potassium hydroxide, the sodium ions and potassium ions, they are the spectator ions, they do not take part in the reaction. It is just hydroxide ions which will substitute the chloride ions. Chloride, although they are not in their ionic form here, this is a covalent compound, but still when this OH group substitutes that Cl group, the chloride ions would be produced. So the reaction will take place as follows. Cl group of this halogenoalkane would be substituted by an OH group and chloride ion would be discharged. So right now we have this is chloroethane, and this compound formed as a result of this reaction is ethanol, and the conditions for this reaction were heat and reflux. So this means that if we want to convert during organic conversions, if we want to convert a halogenoalkane into an alcohol, this is the right reaction to carry out. Heat it under reflux with aqueous sodium hydroxide or aqueous potassium hydroxide. That will do the job. I'll give you another example right here. Like if we are talking about this compound, again a similar type of reaction will proceed. See, this compound's name was 2-methyl 2-chloropropane, and the name of this compound is 2-methyl propan 2-ol. So again a similar type of alcohol is produced, and you do not have to change rest of the molecule, just the functional group has to be disturbed, and in the functional group the halogen atom would be displaced by an OH group during this substitution reaction. Okay, we have a question. Will NaCl or KCl be produced? Yes, the answer is yes. See, I have mentioned aqueous solution of chloride ions, and potassium ions and sodium ions were already there. Hydroxide ions would be used up in the reaction. So what would remain in the solution? Potassium ions and chloride ions, halide ions, whichever halogen we are dealing with. So that means the solution is an aqueous solution of potassium chloride or sodium chloride depending on the reagent we used. Okay, substitution of NH2 group, it's called amine group. When NH2 is bonded to any organic compound, it's called amine group. So substitution of amine group into a halogenoalkane, for this the reagent needed is ethanolic ammonia. And what do we mean by that? See, ethanolic means dissolved in ethanol. Just like aqueous means dissolved in water, if the solvent used to dissolve the solute is not water, instead it is ethanol, then we call it ethanolic ammonia. So if we use aqueous ammonia, this reaction will not proceed, but if we use ethanolic ammonia, this reaction will proceed. And the conditions required for this reaction are excess of ammonia and a high pressure. You do not need to know the exact pressure what is being used, you just need to remember that this reaction takes place under high pressure and excess of ammonia has to be there. Okay, now let us take a look at the type of reaction that proceeds, like the reaction. For example, if we are dealing with, let us take a different halogen this time. Suppose we have C2H5Br, this is bromoethane. And we have added excess of ethanolic ammonia and a high pressure is being used. See, this out of this NH3, NH2 minus would substitute this Br minus group. So this would make the organic compound C2H5NH2, and the Br that got out of this halogenoalkane and the hydrogen which remained from this ammonia molecule, they will form bond with each other and produce HBr. So this was bromoethane. When we substituted NH2 group in this halogenoalkane, we got ethyl amine. And this amine produced would also be ethanolic, because ethanol is present there as a solvent. HBr, this is hydrogen bromide gas, because there is no water in this reaction. Okay, the next substitution reaction that halogenoalkanes undergo is a substitution of Cn minus group. See, this Cn minus group, when it is present as a negative ion, it is called a cyanide group. So like if we are using an ionic compound which has this ion in it as the negative ion, then it is called a cyanide group. But when this group is covalently bonded to an organic compound, then it is called a nitrile group. So in order to substitute this group into a halogenoalkane, the reagent that we use is ethanolic KCN. Again, you can use ethanolic NaCN in the place of KCN. it won't make any difference because sodium and potassium ions are spectator ions, they won't take part in the reaction. So ethanolic KCN, this is potassium cyanide. And the conditions are heat under reflux. Again, we have to provide heat under reflux. Why is that? Because heating is required for this reaction to proceed, but again, due to a highly volatile nature of halogenoalkanes, they start escaping from the reaction chamber. We do not want them to escape, we want them to remain in the reaction mixture. So we place the reaction mixture. Now, suppose we are this time the halogenoalkane is chloropropane. This is 1-chloropropane. Again, in the reaction, only cyanide ions will take part. Potassium ions are the spectator ions, they won't take part in the reaction. And the inside of this cyanide ion is like this. There is a C triple bond N, and there is 1 minus charge on this radical because carbon atom has already gained 1 electron. Nitrogen's valencies are complete. So this again, this is ethanolic, and we are heating it under reflux. Now in this case, Cn negative will substitute the halogen from the halogenoalkane. So C3H7 Cn will be produced and chloride ions would be discharged. So again, there are potassium ions already present in the reaction mixture. So in reality, what is formed is potassium chloride, but as potassium ions were spectator ions, they were not taking part in the chemical reaction. So we may or may not write them in the equation. This product formed will again be ethanolic, and even this will be ethanolic because there is no water in the reaction. Okay, now this compound formed, it has 4 carbon atoms in total. See, initially the halogenoalkane that we used had 3 carbon atoms in it, but the organic compound formed has 4 carbon atoms in it. The name of this compound is butanenitrile. See, this functional group, when present in organic compound, this functional group is called a nitrile group. So the compound formed is a nitrile. It would be named like this. This is butanenitrile because of presence of 4 carbon atoms in the compound. But initially we used an organic compound which had 3 carbon atoms in total. So that means this reaction is increasing the number of carbon atoms. Like if we are converting a smaller organic compound into a larger organic compound with certain specific functional groups, we may have to increase the number of carbon atoms in the organic compound. And whenever you are asked to do that, always use this reaction. First, convert that organic compound into a halogenoalkane, and then use this reaction. Heat it under reflux with ethanolic KCN. Cn group would substitute the halogen group, and number of carbon atoms in the compound would be increased. So this is the application of this reaction, and this is a very important application. Okay, we have a question that is it compulsory to show triple bond of C and N in the formula? No, it's not actually. See, this is a structural formula, so you don't have to draw the triple bond. I drew it because I wanted you to see what is it like internally. If you had drawn the structure like this, C3H7Cn, that is the correct answer. You don't have to show the triple bond always, unless you are asked to draw the displayed formula. Then it is compulsory to show the carbon nitrogen triple bond. Okay, please note this down quickly, then I'll move on with the mechanism of this reaction. Alright, so the mechanism of substitution reactions, all of them. Yes, guys and girls, the mechanism of this these substitution reactions, the type of mechanism is nucleophilic substitution. Okay, now I explained it earlier that what does it mean by nucleophile and electrophile. I'll repeat that again. See, nucleophile is a nucleus loving species. Nucleus loving species. Now nucleus basically has a positive charge because it contains protons and neutrons. Neutrons are neutral, protons have a positive charge. That means any species which has an attraction towards positive charge is called a nucleophile. Now which species are going to be attracted towards positive charge or the nucleus? See, the species with a full negative charge, either the negative ions, or any atom with a partial negative charge and a lone pair of electrons in it. The lone pair of electrons must be shown when we are dealing with a nucleophile, because the lone pair of electron is the one, whether it is a completely negative charge or a partially negative atom, the lone pair of electrons is responsible for that force of attraction. So this is nucleophilic substitution. It is further divided into, this type of mechanism is further divided into two types. See, one is called Sn1 and the other one, see, one is called Sn2 and the other one is called Sn1. These are the two types of this nucleophilic substitution. Now I will go into detail of each type of mechanism. I'll need more space for that. So let us divide the board into two columns. For example, for Sn2 mechanism, if we are dealing with this reaction, the reaction of chloroethane with aqueous potassium hydroxide, it produced ethanol, methyl 2-chloropropane. It reacted with aqueous potassium hydroxide or aqueous sodium hydroxide with heat and reflux, and the product formed was 2-methyl propan 2-ol, and chloride ions were released. Okay, now this reaction is going to follow Sn2 mechanism, this reaction is going to follow Sn1 mechanism. Which halogenoalkane undergo which mechanism, we'll get to that later. First, let us try to understand what these mechanisms are. What happens when a reaction proceeds with Sn2 mechanism, and what happens when the reaction proceeds with Sn1 mechanism. See, first thing is that what does this Sn2 stand for? This S stands for substitution. N stands for nucleophilic, and this 2 means bimolecular. Now, what is meant by bimolecular? See, the mechanism may take place in a single step or 2 steps or 3 steps or even more. But one of the steps is the slowest one, and the slowest step is called the rate determining step. Why is it called the rate determining step? Is because the rate of the reaction depends on the slowest step. The fast steps would proceed in no time, but the slow one would take a lot of time, so the overall rate of reaction is depending on the slowest step. So that is why the slowest step is called the rate determining step. Now, if in the rate determining step there are 2 reactant molecules involved, that means the reaction is bimolecular. I am repeating it again. In fact, I would write that down. If the rate determining step involves 2 reactant molecules, then it is called bimolecular. Then the reaction is called bimolecular. Now for Sn1 reactions, S again stands for substitution, N for nucleophilic, and this 1 means unimolecular. And unimolecular, again we are talking about the rate determining step. If there is only 1 reactant molecule involved in the rate determining step, then the reaction is known to be unimolecular reaction. Okay, now the features of Sn2 mechanisms are a little different from Sn1 mechanism. See, first thing is that now we know that the rate determining step involves two reactant molecules. The second thing would be that this mechanism is a single step mechanism. And the products formed are always inverted. You will get to know what that means when I draw the mechanism. It is 100% inverted. The features of Sn1 mechanism are different. First thing is that it is not a single step mechanism, in fact it is a two-step mechanism. And the second thing is that the product formed does not have to be inverted. 50% of it is inverted and 50% of it is normal. Okay, now one by one let us take a detailed look at these mechanisms. For example, for Sn2, I am going to elaborate the mechanism of this particular reaction. See, originally there was this chloroethane. It would react with these hydroxide ions, and now this time when I am drawing the mechanism of a reaction, I am showing this hydroxide ion as a nucleophile. So I have to show this lone pair of electrons. This pair of electrons would be involved in the bonding. Okay, now see, this carbon to chlorine bond is a polar bond. As we know, chlorine has a higher electronegativity as compared to carbon. So this carbon atom will have a partial positive charge and this chlorine atom will have a partial negative charge. This hydroxide ion is negatively charged. So there will be a force of attraction between these hydroxide ions and this carbon atom. So this oxygen from the hydroxide ion will attack this carbon and share this pair of electrons with the carbon. So we have to draw a curly arrow for the movement of this electron pair. So that curly arrow will be started from this electron pair, of course, but it will have to go around this hydrogen and then end to this carbon atom. I cannot take this arrow straight here from this electron pair to this carbon atom from this right side. Why is that? Because there is a partial negative radical attached on this side of the carbon atom, and between these two negative radicals there will be a repulsion. So this arrow has to move around the hydrogen and come from the back side of the carbon atom, just like this. And when this electron pair starts being shared between this oxygen and this carbon, this electron pair which was between the carbon and the chlorine, this starts moving towards the chlorine atom. So basically what is happening right here is like this. See, this is the carbon atom in the middle. At one side there is a hydrogen, at another side there is another hydrogen. These are the radicals which are not changing. At another side there is a CH3 group. I will draw these three radicals like this. Now at the same time, see, when chlorine is detaching from this carbon, at the same time these hydroxide ions are attaching with this carbon. So I have to draw two dotted lines. on each side of the carbon atom. This dotted line shows that the bond between carbon and chlorine is being broken, and this dotted line shows that the bond between carbon and this oxygen is being formed. These two things are taking place simultaneously. One bond is being broken and the other bond is being formed. So this is not a neutral, this is not a stable compound. This is in this diagram we are just showing something which is happening. This is not a molecule, this is not the formula of a molecule. So this is not a step, it is still continued. And now what happens is that this carbon atom forms that bond with oxygen which was being formed right here, and the bond with this Cl is broken off, and Cl negative chloride ions are being produced. Again, I want to show chloride ions as the nucleophiles, so I have to draw this lone pair of electrons. Now look at this molecule. This molecule is an inverted molecule as compared to what the organic compound was in the beginning, because OH group cannot form the bond exactly from the side where halogen was bonded. This is because of the negative repulsion. It will always attack from the other side, so the molecule formed will be inverted like this. This happens in the Sn2 mechanism. This is why I stated here product formed is 100% inverted. Now let us move on to the mechanism Sn1. And as we mentioned earlier that it is a double step process. It is a two-step mechanism. So let us take a look at the step 1 first. In the step 1, see, this was the halogenoalkane, and this halogenoalkane alone takes part in the step 1. Hydroxide ions are not involved in this first step, and due to presence of a polar solvent, which is in this case water, due to presence of this polar solvent, a heterolytic fission takes place in this bond. That means again chlorine is partially negative, this carbon is partially positive. This electron pair moves towards the chlorine. As a result, the species produced are these. This carbon will have a positive 1 charge and this chlorine will have a negative 1 charge, and it would form chloride ions. Now this step did not involve a lot of some extra forces or extra radicals in it, so it had to produce ions on its own due to just presence of a polar solvent. That means this step is a slow step. Now moving on to the next step. In the next step, this species formed is called a carbocation, in which there is a positive charge on the carbon atom. This is carbocation. Now in the next step, this carbocation will face the chloride ion. Will face the hydroxide ion. See, hydroxide ions comes for the first time in step 2. This is step 2. Now these hydroxide ions have this lone pair of electrons and they have a negative charge. So this pair of electrons will attack to this positively charged carbon atom, and this time we do not have to take the arrow from the back of the carbon. We can simply take it from the front, because there is no negative radical there to repel these hydroxide ions. It is that the negative radical was already detached. So this will form a bond with this carbon atom, and the product will be obtained this is the exact same product. This is 2-methyl propan 2-ol. So now this step, the second step, it took place because of the electrostatic force of attraction between two oppositely charged ions, which is a very strong force of attraction. So this step is not a slow step at all. This is a very fast step. Okay, now let us try to justify the features that we stated earlier. One of them was that Sn2 is a bimolecular mechanism, which means that there are two reactant molecules involved in the rate determining step. And this mechanism involves one step only, and there are two reactant molecules involved in that step. So this is a bimolecular mechanism. And Sn1, there are two steps in Sn1 mechanism. One of them is the slower one, step 1. Step 1 is the rate determining step of Sn1 reaction mechanism. And in that mechanism, only one reactant molecule is involved. There is no hydroxide ions in the reactants in step 1. They show up in the second step only. This means it is a unimolecular mechanism. Next thing is that this is a single step mechanism and this is a two-step mechanism. We have seen both single steps and two steps. Now product formed in this is 100% inverted, and that was because when one nucleophile was making a bond with the carbon atom, the other nucleophile was breaking its bond with the carbon atom, and these two things were taking place simultaneously at the same time. This is why the molecule had to be inverted. Two negative radicals could not be on the same side because they have repulsion to each other. But in this case, in the first step, one nucleophile was detached. The other nucleophile attacked the carbon atom in the second step. This is why it did not have any restrictions about which side to attack from. So this justifies the statement that 50% of the product is inverted and 50% of the product is normal. So basically, whichever side comes in contact with this nucleophile first, it will go and form bond with that side. It does not have to follow a specific route because there is no negative ion there to repel them. So this is how these mechanisms take place, and these are the mechanisms for all the substitution reactions of halogenoalkanes. Now when there is going to be an Sn1 substitution and when there is going to be an Sn2 substitution is very simple. You need to remember this, that the primary halogenoalkanes, now that you know the classes of halogenoalkanes, primary halogenoalkanes always undergo Sn2 mechanism. Tertiary halogenoalkanes always undergo Sn1 mechanism. See, this is why I used different halogenoalkanes for the examples of these two mechanisms. For Sn2, I chose this halogenoalkane, chloroethane. This is a primary halogenoalkane as this carbon atom is bonded to two hydrogen atoms. But for explaining Sn1 mechanism, I chose this halogenoalkane. This is a tertiary halogenoalkane. See, this carbon atom involved in the functional group is not bonded to any hydrogen atoms directly. So this is a tertiary halogenoalkane, and tertiary halogenoalkanes always undergo Sn1 mechanism. You have to remember that. Now what about secondary halogenoalkanes? See, secondary halogenoalkanes can undergo both these mechanisms. So if you are asked to draw the mechanism of a reaction for the substitution reaction of a secondary halogenoalkane and you are not given any clues in the question about the type of mechanism, then you can draw the mechanism of your own choice. But that does not happen very often. What happens is that if there is a secondary halogenoalkane involved in the substitution reaction, they give you some clue in the question, like they say that there was only one molecule involved in the rate determining step. That means they're talking about Sn1. Sometimes they say that a single step mechanism took place. That indicates us the mechanism is Sn2. So they give you clues in the questions that which mechanism you have to follow. But secondary halogenoalkanes undergo both the mechanisms. So this was all for today, but the reactions of halogenoalkanes is not complete so far. So we'll have a part 2 of this stream tomorrow. Hopefully I will update the timing. I will share the timing with you, what time I'm going to stream live tomorrow. But that would be a part 2 for the reactions of halogenoalkanes. That would also include the reactions of nitriles, which were produced in a reaction in these reactions of halogenoalkanes. So I'll see you tomorrow. I hope this video was helpful. In fact, I'll give you a few seconds to note this down. After that, I'll cut off the stream. If you have any questions, you can ask me now. So guys and girls, I'm not seeing any questions. So that would conclude today's session. I will call it a day. I'll see you in the next live stream. Hopefully tomorrow I will update you with the new timing. Hope this video was helpful. Keep on watching Infotainment Lounge. Thank you. Allah Hafiz.